So I'm going to talk a little bit about chiplets from how did we get to where we are now and where are we going in the future? The joke's over. I basically was going to surprise everybody with this, but basically we're here to talk about chiplets, and so I just thought this was a cute way to go by it. But I'm going to be talking about why chiplets and why they're happening now, and then a little bit about the current status, talk about chiplets for saving costs, and then give a little bit of a forecast for that. But it's interesting that you can actually trace the chiplet stuff back to Gordon Moore, who back in 1965 wrote the famous paper about that predicted that the number of transistors per chip was going to double. At that time, he said double every year for the next 5 years. And he then went back and reviewed it in 1975 with another paper. But anyway, Gordon Moore did the magic. This is from his Moore's Law paper. The number of transistors are going to double, and he put it out through 1975. So he looked at that again in a 1975 follow-up to his 1965 paper, and broke down what the things were that were allowing the transistors to increase on the chip. And one of them was the size of the process geometry. Another one was the size of the the size of the die. Anyway, that was his thing about the die size contribution. And then he said the last one was cleverness. And everybody in this room is very clever, and so I'm sure that you've all thought of ideas about making things work better. But that has worked for the industry for a long time. But the trouble is that we're against a reticle limit that is limited mostly by the cost of photolithography equipment. EUV machines are over $100 million. A piece, and so not very many people can afford these things, and the development costs of making one that can do a larger reticle size is really prohibitive, and so we're probably stuck with an 800 square millimeter die size as being the largest thing that could be made. So Moore anticipated chiplets in 1965. He said that it may prove to be more economical to build large systems out of smaller functions which are separately packaged and interconnected. And he did a really good job of forecasting that this was going to happen, but there's certain things that he didn't forecast. He did also forecast the number of transistors going up. This is the average chip density according to WSTS figures over time. And you can see that there's another axis over there on the other side. This is the price per gigabyte. But the natural advantage of this is that the price per function, the price per transistor, price per gigabyte in this case, because it's memory, it does tend to go down, based on the fact that those chips are there. And the whole economics of the semiconductor industry are based on the fact that the prices are going to continue to go down. If the prices ever stood still, then the industry would have to rethink its business. But what he didn't predict was, he predicted the wafers would be 57 inches in diameter, or 1.5 meters in diameter by 2000. And that you can see that didn't happen. It got up to 300 millimeters and pretty much stopped there. So there's certain things that he predicted that didn't really turn out the way that he was expecting them to. But it did, all of this did kind of come together into causing chiplets to happen. And so we've got chiplets today. Some examples of that are, we've got the Xilinx, the AMD's Xilinx division, Versal and Vertex FPGAs, where you've got the Versal both in a chiplet version and a version that has both chiplets and HBM. And it's a little bit hard to see in this. But they were one of the pioneers of using chiplets to get very large chip integration, and also to get some flexibility into the FPGAs that they sold. Because in these ones that don't have the HBM in them, and even in the one on the left with the HBM, you can see these very tiny lines. These the chiplets in this case are actually bars that are not square. They're about 3 times as long as they are wide, and they've been using that very successfully for over 10 years. But there is HBM with some of these too. HBM has become a big factor in this. And so I'm going to talk a little bit about HBM here. And it's an interesting thing. This is a slide I used at the Flash Memory Summit before. What is HBM? And most people think I'm going to talk about the number of chips in that, but no. It's 6 times the price of DDR5. So it's expensive. It is only used for AI. Not really, but you know, that's the impression that most people have. It is a fast-growing market, and it's sold out through 2025. So, you know, those are 4 things you haven't heard of before when people are describing what HBM is. What they usually talk about is stacks of chips, and they show these things which are taller than they are long or wide, but that isn't really what HBM is like. This is a close-up of, actually it's not HBM, it's a predecessor to HBM, it's Micron's hybrid memory cube. You can see that there's an awful lot of area, but not an awful lot of thickness in these things. They are stacked, but they aren't stacked the way that most people draw them. We've got an upcoming report on HBM, and so if anybody's interested in working with us on that, you know, do contact me sometime at the show and let me know about that. But, you know, the HBM, probably the most obvious visible examples of HBM are in the NVIDIA processors, and this is just one of several NVIDIA processors that are using HBM. And you can see it's those gray blocks on the top and the bottom of the golden processor block. Intel is also doing that. Intel has a lot more press photos that are easy to find, and so that's why you get more of them in here. But you can see that they're anywhere from, you know, 6 to 8 HBMs inside of a package for these things. And then even Huawei over in China is doing it. There are, you know, trade restrictions to prevent Huawei from being able to get those HBMs from suppliers outside of China, and so they're trying to develop, the Chinese semiconductor industry is trying to develop a local source for HBM. And then you've got even companies that you might not even have heard of before. This is Sambanova's AI processor, which has 8 HBMs around it. And a lot of these chips are being designed by a company, Broadcom, which is mostly known for being in communications chips. But they do an awful lot of design of HBM-based things for other companies. The companies hit them with an architecture. And, you know, examples, they won't, you know, admit, or, you know, they won't disclose the name of their customers, but Google, I believe, is a very large customer of theirs with their TPU architectures, where Google actually gives them an architecture, they embody it in silicon, and then put it together for them. And so, oh, I got ahead of myself. This is another communication firm. This is Juniper, and they're a networking company, and they've got HBMs inside their things. This is a version of the Juniper Express, and once again, they're using chiplets to be able to define how they're doing things. Okay, so here's Broadcom's design that, you know, this is just one design that they showed off of something where they've designed chiplets and HBM all together in something, and this one's got 12 of them. I don't think that I've ever seen anything that is a real product with 12 HBMs in it, but, you know, it certainly could be the path of the future. But, you know, this is all high-end stuff. All of these are $10,000 and more expensive processors. And in the future, I'm expecting to see chiplets come out in the low end too. And just as an example of that, I have a pen. I'm sorry, they're not only for high-end applications. Okay, so the glory applications, the ones that you hear of, are $10,000 processors, and these processors tend to require very large die sizes, and also the Xilinx FPGAs that I was pointing out to you that didn't use HBM, they also use very large die sizes. But some of them use specialized chips like HBM, or AMD uses I/O chips with some of their processor chips, and some of them use separate chips for doing power stuff. But, you know, can it ever migrate to the low end? Well, it seems like there are cost issues in doing it with the advanced processing that Jawad was talking about, but also yield concerns. When you're working to make something really cheap, then can you stand the kind of yield worries that you have with a regular high-end thing? And then is there even a need for something like that? Well, I found one. So we're already there. This is a pen that was given to me by the Humane Society with the hopes that I would hit them back with a big cash donation. This pen actually has heterogeneous integration in it, where they're using multiple chips so that they can use different process technologies. If you look inside, there's what looks like a very normal LED. There's an MCU, though, inside this package. And if you look, you can see some wires going over to what looks like another chip. That's actually 3 LEDs. You've got a green, a red, and a blue. And all of those LEDs use different technologies. So they're all built using different processes. And the MCU is built on silicon. And so it uses different process technology too. This is an example of the heterogeneous integration that is also being used, for example, when DRAM HBM stacks using a DRAM process are teamed up with an advanced logic process inside of an AI processor. So there's a big gap between this particular application and those other applications that will be filled over time. And so chiplets will be used for cost savings. We've got a new memories report that's coming out that you can look back at the slides if you want to find out more about that or talk to me about it. But emerging memories, this is MRAM, resistive RAM, phase change memory if it gets there, ferroelectric if it gets there. Those technologies are a really good way to take that whole idea of having different processes and having them work into things. And so we use an example Intel processor that has logic and SRAM where we say, what if we divided that into something else? And the reason why you'd want to do that is because SRAM doesn't shrink just linearly with the rest of the chip like you'd expect like this, showing that. But instead, it's shrinking at a slower rate. And so you can see the SRAM becomes a larger part of the overall processor over time, and that prevents the processor chip from getting small. And processor chips are really expensive silicon. And so the idea is if you use a chiplet and you, instead of using logic and SRAM, you use logic process for the processor, SRAM for what's necessary to do it, but then DRAM and MRAM for the other things as separate chiplets, you'd end up getting a much less expensive processor. And particularly MRAM, because MRAM is a single transistor device as opposed to the 6 transistor SRAM. And so it gives you larger effective die sizes, and the MRAM would also give you persistence in the CPU. So I'm not going to work through this whole thing because I chewed up all of my time learning to push buttons. But in a chiplet forecast, we look at that, we say, okay, there's one concern, and that is NVIDIA's revenues have taken off because of the AI craze, and all of the hyperscalers are spending like crazy because of the AI craze. Is that sustainable? And the way that I checked to see whether or not it was to say, are revenues keeping pace with this great investment in AI that the hyperscalers are making? And it's not. You can see that they've gone from being on average about 12%, that 12% of their revenues are going into capital spending for the past several years. And then all of a sudden they've zoomed up to 17%. You know that that's going to get a lot of pressure from stockholders for these guys to try to cut their capital spending some. And so we're expecting sometime this year to see capital spending on AI at hyperscalers to drop back down again. And with that in mind, then we look at it, we say, okay, well, that's probably going to calm things down. And so we've got a not too fast move in here, but we also are saying that chiplets are going to migrate down to a lower level. And so because of that, we're saying that by 2030, the good time from now, we're going to see probably about half of all semiconductors use some kind of a chiplet thing if you count in things like my pen example.